Hello everyone. So for today's stream, I've actually gone ahead and coded everything that we're going to be covering today already. And this is because it's actually getting pretty complicated now. Uh, but hopefully we have some very interesting things to show. Uh, so the the last time we covered the paths. We defined a whole bunch of equalities for paths and showed that it was a partial equivalence relation. And then one of the things that I mentioned that we wanted to do this time was this list of nodes here. We wanted to be a a proper set of nodes instead of saying that it's a list, because we want graphs that have different lists but are covering the same nodes. We want them to be equivalent. So we want to change this node into a set of nodes. And so there's a lot of boilerplate that we need to do for defining a module for nodes that determines that it's something that we can use to build sets from. So we'll be using the msets library. So require import sets. And the within this, it gives us this module that we want to define called sets. So print module type sets. And we see that a set is this has this signature where we have this T, which represents the type of our sets, and alt or element that represents the elements within the set. And it has all these functions like a singleton or empty to define sets, and operations on these like the union, sort of intersection, or difference, all of these things to manipulate sets. So we want to be able to define the sets for our definition of node. So we need to construct a data type of that has the signature for our particular node type. So the way to do that, there's this within the msets, there's this a functor called make. And what this does is it takes in anything that like any module of order type and provides you a the signature of set. So we input in anything that is ordered, and it'll provide us a way of creating sets of that type. So that means that we need to prove that node is an ordered type. But as we have it right now, we don't have any information about node, so we're going to have to make some assumptions about node. So how do we prove that it is an ordered type? We need to take a look at what are the things inside of ordered type. So if we take the instruction of print module type order type, we see order type is anything that has these things being instantiated. And we'll be covering these more detail. But for now, let's just copy all of these things and paste them in underneath node. So we would like the uh, to create a new module node ordered, and we want it to be of the order type. And we want it to have these things within the module being defined. And then we end node ordered. So this gives us an order type for nodes, but we need to do a bit more things to be able to, like right now we're just assuming that all of these parameters exist. We want to attach it to things that we actually define. So we want this t, basically the type of the things that we say are ordered. It's not a parameter, it corresponds to the node that we defined. So definition it corresponds to node. So this should still work. The other thing is we want this t being node to be visible from seeing that we have a node ordered, because right now if we print node ordered .t, I think this is will show us, yes. It tells us that it doesn't know what the type is. And this is like with a module, when you put something, a definition within the module, you're doing like an abstraction to say that the thing inside of the module is hidden. You don't actually know the implementation. But in our case, we want to be able to see that this order type is exposing the particular t, the definition of t, to be node. And so instead of doing this colon here, we want it to be this less than or equal to colon. And that's going to say that we want the module to have all of these things being publicly available. So now once we get down to here and we do the print, we see that node ordered.t is equivalent to node. So it's no longer hidden from us. And so when we do the sets, we can put the nodes inside of the sets. Now, we do have a definition of equality for the nodes. It's just the default one built into Rocq. So we can define it as that. And the way to do that is at EQ, and we give it the type node. So this is just like the built-in definition of equivalence within Rocq. And with that, we want to show that EQ is an equivalence. And this is just obvious from the way that Rocq defines these things. So we should just do, this is a instance, similar as how we did last time, where equivalence is an instance. So there's a type class that is attached to this EQ that we defined here. So we will do instance EQ, and it tells us that we need to prove that it is an equivalence. But this is so obvious that if we just say that it's underscore, Rocq is able to figure it out for us. Another way to do this, there is a, we can say program instance. And with that, it actually runs some tactics when we define this to be able to try to simplify the thing that we need to prove a little bit. And because it's so obvious, it managed to figure it out for us immediately. The other thing that we need is this less than. This is saying it's a property that compares two different nodes and determines when one is less than the other one. So the with less than, we like, the idea is that for an order type it's ordered, and so the way that the set is constructed is by doing a sorting on the elements of the set. And so the set is still basically a list. It could be a more efficient data structure than a list, but it's equivalent to a list representation where everything is ordered. And uh, since it's a sorted list, anything that has the same members is going to be equivalent. That's basically why we need the order type within the set. So we do a comparison for less than for all these nodes to be able to do this sorting. And we have this parameter down here that less than compat, a proper EQ, if and only if less than. So this is another instance. So if we do program instance here, we see that we have this obligation remaining to be proven. So let's take a look at what that is. So next obligation brings up into focus this obligation that we want to prove. So we need to prove this now. And if we look at how this is defined, I did some digging in the to figure out what that actual definition is, and it is called respectful. So unfold respectful. Yep. Oops. So we want to show that if x is equal to y, and if x0 is equal to y0, then if x is less than x0, then y must be less than y0. It's basically composing this less than over the equality, converting the equality from x to y and the equality from x0 to y0. And because of our equality being defined as like Rocq's internal definition of equivalence, this should also be a obvious fact. So why isn't the program instance able to figure this out? We need a little bit more of a stronger tactic for it to run whenever it reaches this this goal. So the tactic, as I found within the way that order types for nats are defined, is this thing here. So the simple relation here is a tactic, and we are stating that it's a whenever we find an obligation in this local scope, we will also run this simple relation to try to solve it. So now program instance less than compat will try running this tactic, and oh, of course, yes. So the other thing that we need is equality. Oh, we need to be able to unfold this equality everywhere so that it can see that underneath it is this actual definition of the internal equality. So a trick that I found to do that, like it's still not working right now because we still have the obligation. But if we move this definition from over there to the very bottom, so now this EQ here is going to be defined as the EQ here because this one overloads the definition of EQ. So if we use like the built-in definition of equivalence, then we should be able to solve this part. So we just need to specify in here that because EQ has not been defined at this point yet, we need to specify that it's the other one. So this first one is still able to solve. And then when we introduce the less than and add this tactic here, and then we run this, now it's completely solved. Because this EQ corresponds to this one directly, instead of corresponding to this one that needs to be unfolded. There's probably another tactic that would also unfold this EQ. Maybe if we... I'm going to try something. I didn't try this before, so this might not work. Unfold EQ. And simp relation. So now let's see what happens if we put this above. Yep, that worked. So maybe we can revert back to this definition here, and we'll see what happens. Does this work now? Yep, that worked. Okay, that might even be cleaner. So I changed the tactic into unfold EQ. I guess I should also do a try in front of that in case EQ has not been defined. I don't know if that's going to happen, but yeah. So now this EQ is referring to this EQ, but we wanted to refer it to this EQ. So doing the unfold EQ here should unfold it into this version. So we're putting in the correct EQ. We still need to leave this one as a parameter because we haven't provided an actual definition for less than. And we need to specify that whatever definition we provide is going to have this property. So we left that as parametric, as a parameter. That basically just offloads that work to whoever wants to define the definition of node. They're going to have to provide all of these parameters. Then comparison, I suppose there might be a way to define comparison from the less than and the equality that we have. What comparison is, it's basically, it gives you three different options. It's either going to be an indicator for less than, an indicator for equal, or an indicator for greater than. So compare operates on its two inputs and gives you the indicator for those three types. And compare spec, zoom out a little bit, it's going to see this is the case for equal, this is the case for less than, and this is the case for greater than. And the result of running the compare y, compare xy, will give you things that match up to each one of these. Oops. So whatever definition of compare that we have, these properties should be true. And we're going to leave those as parameters. We'll offload that to either some later day when we initialize node to be something, or we could always leave node generic and leave these as just assumptions. The last assumption that we need to make is that equality is decidable. Basically, this means that for any two nodes, we can decide whether the node x and y are equal or not equal. This is not inherently known from equality itself because we are in the constructive setting. We need to provide a proof of it being equal or not equal. But we say that for this particular test, we do have equality being decidable. So with that, we have that we have defined node ordered for our definition of node, and we have derived that node is an order type. From that order type, we can use the make that we had before. Guess I'll delete these print modules from here. And we add the line of module S. Here we're defining a new module named S. And we're going to construct it from the functor make using the module as input node ordered. So now module S has been defined. And we can check what is inside of it. We printed module type S. It corresponds exactly to our desired thing of the sets, where this parameter t represents the type of the set, and we have element. And if we unroll the definition of alt, let's see if this works. Print s dot alt. It finds that the elements within the set are nodes, which is exactly what we want. Cool. So now we defined the type of sets of nodes, and we can update our graph to, instead of list.node, we have s.t, which is the set of nodes. So nodes is now a set of nodes. And of course, stuff is going to break from there. The in was defined for lists. We instead, I'll do a search here. And I'll replace it with the s.in. So it looks very similar to how it did for lists, but now it's within this module S. And now everything should work. Cool. We have redefined everything. Everything is looking good. And we're doing it in terms of this new set instead of lists. That took a lot amount of time of digging through and finding what all of these things meant. So as an easy point of reference, I can always look back at this video and see the exact steps that I did to figure out what is the command to print out the thing that I need for this module, and then define everything within that module. And yeah, but otherwise you could go digging around in the library definitions to find something similar. The one that I used was I found the module named nat as OT, and that defined a lot of these things similarly. So I based my definitions similar to that. Okay, so now why did we go through all this effort? We now want to do graph induction. We want to be able to induct over the set of nodes and say that if we have a property for all smaller sets of this graph, then we should have the property for the larger set of the graph. So let's go to right underneath graph. And we want to define our own method of induction over graphs. So let me copy that from what I have. So we want to, we could do like a lemma and graph ind and everything from there. But that's, we wanted to be able to run with the induction tactic. And the induction tactic recognizes whatever we define when it's sectioned off in this separate section with variables and hypotheses. So we're actually going to go ahead and define the whole section. section graph int. So this graph int opens up a new sectioned off piece of code. We can define anything that we want to define in there, and to refer to it, we just call it from within this. It's similar to a module. Then the thing that we want to define within this is we have some property variable p that goes from that has a graph as input and provides a prop. So this is the property that we want to prove. And we want to end with a definition graph int of for a particular graph G. We want to know that P of G. Cool. So we clearly need our induction hypothesis for this as well. We can't just say that an arbitrary P holds for any graph. So we need a way of inducting over G. And our induction hypothesis is going to say for anything that is a subset of the nodes, if we know that P holds for any subset of the nodes of the graph G, then it will hold for G. How do we say that? So hypothesis IH. So for all the graph, which is the overall graph that we want to prove, then we have something that needs to say P holds for all strict subsets nodes G. Then P of G holds. Okay, so we have described it verbally, but we need something to fill in there mathematically. So let's define a graph that has a strict subset of nodes. So for all G prime graph, we need to know that it is a strict subset. The nodes of G prime compared to the nodes of G. And then we want to know that P of G prime holds. That wasn't too bad to change into this, but now we don't know what strict subset is, and unfortunately the nodes the set library doesn't actually provide us one. But we can define it pretty easily by stating that something that it does provide us is subset. So strict subset for any two inputs of s dot t, so any two sets A and B of nodes, and we want to compare it's a proposition. So it does provide us with the function subset, which tells us that this set is a subset of B. And so we just use that it's a subset in one direction, but it's not a subset in the other direction. So there's something within B that is not within A, but everything within A is within B. That's our definition of subset. Right there. And we should get down to our definition. I'll do admitted for now. And then we need to close off our our section here. So we can't just leave this as admitted. We need to figure out what we need to fill in there to be able to define it. So to do this induction where we are doing over the strict subsets of the graph G, we can do an even stronger induction where we're doing induction over the size of the set of nodes, so like the number of nodes that we have in the graph, and we prove it for all graphs that are smaller than that. So in here, I guess if we want to prove P of G, we just apply the IH. This matches up for this. Apply IH. And now we need to prove this smaller goal that says that it's a strict subset and it still holds for P of G. Intros G prime H sub. So we have that is a G prime is a strict subset of nodes G. We need a way to prove that P of G. So we would like to just call graph int again on this thing. But we can't actually do that. So to grab a reference to the function itself so we can call itself, we change it to fixed point. So now if we look at the thing that we want to prove, we have graph int where we can call this function itself from within the body of the function. That works for any graph G. Then we do apply graph int in here. And we are done. So let's try doing defined here and see what happens. Yep. So unfortunately, just doing this basic mechanism, it gets confused because graph int needs to operate on something that is strictly smaller than the input graph. So like if we had tried to just do apply graph int right at this top here, that would work. It type checks because we are applying the function to its own inputs, but it will infinitely loop because we are just taking the argument and putting it back in. So to prove that it doesn't infinitely loop, it does some extra checks to make sure that it is smaller than the input that we put in, by some definition of smaller. And when we do it down here on this G prime, it should be smaller because we know that it's a strict subset, but Rocq is not smart enough to be able to figure that out right away. So we need to do some transformations to be able to teach it that it's okay. And this is where I mentioned we want to be doing induction over the length of the basically like the size of the number of nodes, which is a bit stronger than we want for our induction hypothesis, but it will get us there. So how to specify that? We want to state that the measure, basically the thing that we're measuring every time in our recursive call, is another way to do this is with well-formedness, and but measure because we're going to be using a natural number. So measure, and the thing that we're measuring is the s dot cardinal nodes G. S dot cardinal is the way to acquire the length of a set, or the size of the set. It's the cardinality of the set. Then the nodes G is the set that we're trying to analyze for any particular input G. And this gives us a natural number. So Measure is able to find that natural numbers are compared by the less than operation, so it puts that in for us, but you can also specify that more precisely. So with this, it brings up this well-founded less than cardinal nodes G, and it's basically, we want to be able to, knowing that this less than operation is well-founded. Well-foundedness just basically means that we can do induction over it. That less than will give us a smaller and smaller definition as we go down on the natural numbers. Like if a natural number is less than 1, it's less than another natural number, then it is smaller than it by some definition of, like, it's constructed to be smaller. And it will eventually terminate when we hit 0 for the natural number, because 0 is less than any other natural number. And so like our induction is basically going down the less than until we hit 0, and then we're done. But we don't want to see these well-foundedness goals anywhere in our proof. We sort of want to hide them. And thankfully, we're working with natural numbers, and natural numbers have these well-founded principles already established. So we just need to find them. And we do that by saying, adding the word program in front. And this, yeah. It says that it requires a body. So I'll just say that the body of the function is underscore, and we'll want to prove it later. Yep. And it says that the well-foundedness thing is not registered, and we want to import something to be able to find the well-foundedness of natural numbers. So we're going to not do the particular library that they tell us here, although that might work. We instead just do require import program. And now the well-foundedness of less than should be loaded in. And when we do program fixed point here, it'll be happy. Yep. So we initialize it, and we have one obligation to prove. So next obligation. And we still have the same thing that we want to prove before, but now to apply graph_int, it's changed to being if we can apply graph_int on any G0 such that the cardinality of G0, the nodes of G0 is less than the cardinality of the nodes of G, which is exactly what we want to have. Okay. That might have been quite a lot of information, so I'll recap it a little bit. We want to prove an induction hypothesis over graphs. So we define this new section where we define our the P that we want to prove inductively over, and IH, which is our induction hypothesis, which states that for any strict subset of the graph, we know P holds. Therefore, we have a way of constructing that it holds for the larger graph. This is the thing that the user will have to prove once they're doing the induction over the graph. We can build up a proof from the smaller subsets of the graph. Then graph_int is the induction property that we want to prove, and we want to know that P of G, that this property holds for this graph G, using the induction hypothesis. And the way to prove that this graph_int is able to do that is by defining it inductively based on the cardinality of the number of nodes inside of G. This way we have a natural number associated with the depth of the call, and every time we go down, we're decrementing on the cardinality of the nodes, at least by 1. So we cannot decrement more than 0. So once we hit 0, we'll be done. Essentially, once we hit 0, then this statement here that all strict subsets of 0 is going to be vacuously true. So we can just directly apply the induction hypothesis for the base case. We're basically describing the base case by this well-ordered measurement. So we need to finish off proving that like the body of graph_int, because we just left it as a underscore as the placeholder, and so we need to fill in the definition. So like before, we want to prove PG. So we apply the IH, which gives us a final proof of PG. So now we introduce the things, and we have a G prime such that it's a strict subset of G, and we want to figure out that P of G. So we apply our graph_int on this G prime because we know that G prime is going to be smaller than G. So now we need to prove that it is smaller than G. So we have left to show that the cardinality of nodes G prime is less than S dot cardinal nodes G. Like the cardinality has been decremented. We basically want to show that from strict subset, this property is true. So let's abstract it out into a separate lemma. I'm actually gonna copy paste that lemma definition. We want to prove that for any two A and B sets, if A is a strict subset of B, then the cardinality of A is less than the cardinality of B. I'm going to leave that as admitted for now. Yep. And so we should be able to finish off this graph_int here to show that this is actually the lemma that we want to prove. We'll do an apply strict subset cardinal, which is the assumption that we have from H sub. So auto should be able to finish it off. And we are done. We have defined it, and we have proven our graph_int. So let's do a check graph_int. And we see that graph_int, now it takes all of these variables and hypotheses and puts them in these for alls. So for any P that we want to prove inductively over, and as long as we have our induction hypothesis, that for any graph G, any strict subset of G holds means that G holds, then we have proven for any graph G, this property P holds. We have proved that this P holds inductively for any graph that we care about. So we do, if we use the induction tactic, we can specify that we want to use graph_int as our induction hypothesis, as our induction method. And we'll be able to do induction on graphs using these strict subsets, which is exactly what we want to do to prove whether or not there is a path in the graph. Yep. We might need to change from prop to type later, but that's a problem for another day. So for the remainder of today, we just want to prove this strict subset cardinal lemma. It turns out it's a bit messier than we would like it to be, but it still works pretty straightforwardly. So we're going to be doing it from a top to down perspective. I've already done this proof once, so I think it should be a little easier because I don't need to be scrambling to figure out what to do in all of these lines. But it is going to be the most complicated proof that I've covered so far. So we start by introducing everything. A, B, H. And we want to break apart this strict subset into the two parts that we have. So I'm going to introduce it into these two different parts right away. So we have a subset and a subset. So let's take a look at what a subset looks like. Unfold subset in H1. And subset just tells us that for any element of set, so like our node, for any node, if we know that it's in A, then it's in B, for this definition of S dot in. So we want to be able to prove that the cardinality is lessened. So what we want to essentially use is this check no equal length. So if we see this particular lemma, we see that for any set of lists, if there's no duplicates in the list, and everything in the first list is included in the second list, then the length is going to be less than or equal to. So we can convert from this H1 into this incl, and then we know that there's no duplicates within the set, and we'll be able to find that this S dot cardinal corresponds to the length of the list, like A as the list representation. We're going to be doing a bunch of back and forth conversions between the set and the list by converting through the, we do a check S dot, I think that's it. So S dot element just takes us from an S dot T, so like A and B, into a list of elements. So if we prove all these properties over S dot elements of lists, then we should be able to get it for S dot cardinal. So if we don't know what the particular thing is to do here, the way that I figured this out was doing a search S dot cardinal and seeing what lemmas are defined to help us prove stuff about the cardinality. And we see that the only lemma that we have really is that the S dot cardinal S is equal to the length of the elements of S. So that indicates that we sort of need to do everything in terms of S dot elements of S. Let's do a rewrite based on this thing here. Rewrite S dot cardinal spec. And that places this first part, which used to read S dot cardinal A, into S dot elements of A. Then we can do it again to replace the second part. So S dot cardinal of B gets replaced with length dot elements of B. And now we need to prove that it is both less than and not equal to. So we'll do I guess we also want to know that this subset, it implies that everything within S dot elements of A is included within S dot elements of B. So we'll write a helper function for that. Subset info for all. Let me make sure I get this right. for all a b s dot subset a b if and only if incl s dot elements a s dot elements. This lemma is basically telling us that subsets means we have the property of incl over the elements. We're basically just transforming the definition of subset within S into the definition of subset within list, which is this incl. Every incl just basically means that every element of this is in every item in this list is also an item in this list. So I'll leave this as that. That's a proof stub that we need to prove later. But for now, we can rewrite subset incl in h1. So we can replace this subset with the incl version. And we can also do that for h2. So we have incl versions, and we unfold it into the elements version. So now everything is defined in terms of these elements of A and B instead of A and B themselves. So we should have two different assumptions. I don't want to write it all out. So our first assumption is that if we want to prove that it is less than, we prove that it is less than or equal to, and then we also prove that it's not equal to. So we state this. We need to prove this as like our subgoal. I'll leave it as admitted for now. Now we have h3 as our assumption. And we need to also prove that it is not the case, which is the squiggly, it's saying that it's not the case, that they have equal length. So we would admit here. Using the h3 and the h, I guess it turns the squiggly into a not equal to. I guess I should use that notation as well. So if we have that the lengths are not equal, but we know that the lengths are less than or equal to, we should be able to deduce that it's less than. To do these kinds of proofs where we have natural numbers exactly as is here, and comparisons of like less than or equal to, or not equal to, or equal to, or less than, this is usually solved by this tactic called Leah. And of course, we need to import it first. Import Leah. And it should automatically solve it for us. It found that it could destruct these in a particular way to be able to construct that. So Leah. And what Leah stands for is, I believe, is linear integer arithmetic. It replaced an older version of it, which is called omega. Now we use Leah to solve these kinds of goals. So to clean this up, I'm going to do it all in one line here. Try Leah. That basically kicks out this goal down here. So yep. So we only have this one goal that we want to prove in here, so we don't need these squiggly. So let's start with this top one. So we have the two goals to prove, this top one and this bottom one. And we're going to start with the top one. And as we said before, we want to do this thing. Let's see how it's defined again. If we want to prove that a length of a list L is less than or equal to the length of L prime, which is basically this goal that we have to prove down here, then we need to prove that everything is included, which is an assumption that we have over here, and that there's no duplicates in the first one. So we're actually pretty close to finishing this part off. We just do an apply. And we know that this one is just solved by this hypothesis here. So we can just do an auto to clear that one out. And so we have left to show that there's no duplicates in s.elements of A. Unfortunately, if we try to search, we can provide more than one parameter in search. No dup and s.elements. There's nothing that pops up, so let's just look at s.elements and see the whole list of things. And if we look down, we'll find this one here. S.elements spec 2w, no dup A EQ, s.elements of S. And if we look at the definition of no dup A within the library, we'll find that it's basically the same as no dup, but it uses this equality instead of or the built-in definition of equality. But because we have defined equality as the built-in definition of equality, there should be a correspondence there. So I'm going to copy paste another lemma. We should know that there's a correspondence between no dup A and no dup. That for any list L, we fill in the EQ, which is this node order.eq. L implies that no dup of L. So we're basically removing the we're deconstructing it on both sides and reconstructing it so that they are equivalent. They have a correspondence with each other. And we'll leave that as admitted for now. So if we want to prove no dup, we convert it into the no dup A version. So now we need to prove that no dup A node order.eq s.elements of A. So let's find it. And it's right here, s.elements. We'll apply that particular lemma, and we are done with this goal. Cool. So that was pretty easy because we were able to use this no dup encode length from the list library. Another way we could have done this is directly proven this no dup encode length for the particular set that we have. But the fact that we can refer to it from the list library is pretty good. Then we want to prove that the length is not equal to that. And for that, let's look at like what the list library gives us. So we'll look up stuff like no dup and encode. We'll see what that gives us here. So we did the no dup encode length. But if we take a look at this bottom one, I guess like the second one doesn't really help us that much. We already know that both sides have no dup, so that's not going to be helpful for us in this particular case, but sometimes this is a pretty helpful lemma. But this bottom one, the no dup L and length L prime is less than or equal to length L. So it's basically flipped. The ordering is flipped here. Before, like, we had L prime on the right side. This time we have L prime on the left side. And we know that everything in L is included in L prime, which is our assumption H1, then we should be able to deduce that L prime is everything in L prime is included in L. This contradicts H2 directly. So from the fact that we know that if we're trying to prove this thing here, if we do an intro, H4, we want to prove a falsehood from knowing that it's equivalent. Let's open up the lemma again. So we know that it's equivalent here, and equivalence is stronger than saying that it's less than or equal to. So we should be able to prove that it's less than or equal to from this assumption 4. And then we derive a contradiction with H2 because we know that it's not within the elements. There's something within the elements that is not within the other elements. So if we do a contradiction, this negation basically means from this assumption we have false. So if we want to prove false, we can just apply H2. So we have left to prove the thing that is within the H2, this that the elements of B is included within the elements of A. And using the lemma that we have here, no dupe length equal, we can apply that there, and that gets us exactly what we want to have. So we want to prove that there is no dupe, which is exactly this proof that we did before. We want to show that the elements are less than, which we could do from Leah by using this equality. And this thing here is our assumption H1. So let's try an auto to get rid of that assumption. Auto. And then we'll do a try Leah to get rid of this assumption, but not clear that assumption. If we try to just do Leah here, it'll try to apply Leah on both sides, and they'll fail. Couldn't find a witness for the first one. So try Leah. And it got rid of the second goal. Let's see what that goal was again. We want to prove that it's less than or equal to, and we have that it's equal to, so Leah was able to get rid of that goal. So we have left to prove that there's no duplicates. We can just copy paste this in here. I guess we don't need this line here. We convert it into the other version of no dupe, and then we have that. So now we change it from admitted to UED. We have the proof. We're not done yet. We still have these helper lemmas that we defined over here. So let's take a look at how we can define them. Let's start with the subset incl. So intros AB. And here I'm going to unfold the s.subset. I could do a unfold incl as well, just to see how it looks like. So it looks very similar, where we need to change the s.in into in.s.elements, in of s.elements. So these obviously should correspond to each other, but we need to prove it. So this if and only if can be split into proving each side separately. So we'll do a split. And then we introduce the opposite side, and then an element, and then the property of in, and that happens for both sides equivalently. So we'll do a tactic that says do it for both sides, the introduction. Intros each AB and X and HA. So we have these two goals left to prove. They're going to be very similar to each other, but basically in a flipped form. So let's just do the first one. And here, we want to be able to convert from s dot in into the in version. So we need another helper lemma to be able to convert that. Copy paste the helper lemma definition that I had from before. This is fairly similar to everything that we have so far for the no dupe A, but for in A, if we have in A of the node order.eq of this list, then we shall have in A admitted. And the reason for that, if we take a look at the s.in, search s.in, we'll find that s.in gives us this thing here, elements spec 1. S.in implies that it's in A, the elements of. So we can convert via this thing here. Copy the name of that. So what is the thing that we need to prove? We are starting with in for this version. So we do the apply in A in. The fun thing about this apply is that because we have the if and only if, both arrows, it's able to figure out, Rocq is able to figure out which side of these arrows we should apply. So it finds that we have this in A, so it's applying the arrow towards the right. So we have left to prove this thing, and we can apply the conversion to get us s.in, and then we apply HAB. We have s.in, and then we apply it in the reverse order to get us in A. And then we finish it off with the which is something that we have in our assumption, which is HA, so auto, we'll be able to finish this off. So we see we actually created this really nice sandwich. We want to prove that in A, but we have s.in A, an arrow that converts us from s.in A. So we do a conversion from this into s.in A, then we convert it, s.in B, then we convert it into s.in A, and then from that s.in A, we convert it into the hypothesis that we do have. So this is basically a commuting diagram. If you enjoy category theory, we're basically converting into one representation, doing the function in that representation, and then converting back. And of course, the other side is going to be the same sandwich, but reversed. So we're starting with the in, s.in. So the first thing that we do is apply the one, and then the in A. Then we apply this one, and then we do the conversion. So that one changed it from an A to from a B to an A. And then we do the conversion again, and the sandwich is reversed. And then we're done with auto. So that sandwiching was actually pretty cool. So we have proven the subset, but we created an extra helper lemma that NA. So it seems like we didn't get that far as we would like, but we did actually simplify this into a smaller lemma because this NA is easier to prove. But yeah, I guess we'll start with this one at the top. Enclose a L. And we can do this by doing induction over L. So let's try that. Induction L. Because we know that L is a list, so we can do use the built-in notion of induction over lists. And so for the base case, so this thing over here, we just know that L is nil, so there's no assumptions that we need to specify. But for the inductive hypothesis, we have the head of the list and the remainder of the list. So B colon L is equal to this top level L. And then we have the induction hypothesis, IH. So we need to prove these two things, I think. So like we either plug in nil or we plug in B colon L. Simple reduce stuff. Yep. The reductions are set for simple to reduce the inside into false for the nil, and this disjunction for this side. We sort of need to do the same for the NA, but it didn't automatically unfold this with simple. So let's start with the first case, this nil. And we can do a search NA, see what lemmas we have to use. And find that the very first one is NA nil. It changes from this thing that we have into false, or we could just apply this directly. We could do a rewrite to, now we need to prove false with false, or we could just do apply. See if the apply works. Yep, that's exactly what we wanted. Now for the induction step, let's go ahead and rewrite this part here into the IH that we want. Or let's not do that yet. Let's simplify this left-hand side first. So let's search NA, see if there's something in here that can help us. This one seems close, but it's not exactly what we want. This one's again not exactly what we want. But down here, this is the one we want, saying that we have the Y colon L, and that is equal to this disjunct, EQA. Let's do a rewrite of this thing. It first looks like this. After doing the rewrite, we have node.order.eq, node order A of B, disjuncted with this thing. If and only if B is equal to A, we can go ahead and unfold this thing. Because our definition of equality is directly the definition of Roqq's definition of equality, as we defined it. So we have left to prove these two things. And we can actually just do the rewrite IH here to convert that right side into this cleaner version. So now we just have to prove that this thing is true. And we're going to try it all in one line. So we want to prove both sides of this implication, so it's a split. And then on both sides of this, we will have a disjunction that we want to include. So intros h1 or h1. Right, let's call it h or h. And then auto should be able to clear out the in a because it finds this in AL in the context and it wants to prove this disjunction. So it just automatically figures out that it should go on the right side and prove that there. So that covers two of the cases. Actually, I think that should be it. Because it also is able to figure out that A equals B is equal to B is equal to A. Let's see if this chain combo that we did is exactly what we want. Yep. It's very satisfying when we think about all the steps that this proof is going to expand into, and we just deliver the combo and it automatically solves everything, especially if it's on the first try. And this is sort of like the brain muscle that I built up over time, being able to do these kinds of proofs in my head and just do one tactic that solves everything in one go. It's very satisfying. And then we are done, so QED. Cool. And we have proved the conversion between in A and in. And now the last thing to prove is this no dupe. Intros L. And here we're also going to be doing induction, very similar to how we did before. Just do a capital L. So it looks exactly the same as our induction hypothesis from before. So in here, it doesn't actually simplify the right-hand side, so I guess simple wasn't actually used. These are our two goals that we want to prove. We'll start with the base case. So in here, we'll do we could do the same search no dupe when we have a proof that no dupe nil. So if we were trying to prove no dupe nil, then we would be done. And if we do search of no dupe A, we also have a no dupe A nil. So I'll do another chain combo here. This is slightly different than the way that I had proved it before, but we do a split auto using no dupe A nil and no dupe nil. So this will specify that auto is allowed to use the application of both of these to resolve it. When we're doing a split to split apart this thing. Oh, we do need to do an intro, but we don't care about the thing that we're introducing, so we'll just get rid of it. Because we have directly that the nil is a no dupe. So that managed to solve that entirely. Very satisfying. Then we can do the same thing for this side. Search no dupe. And we find no dupe cons here. No dupe cons tells us that if we prove that X is not in L and there's no dupes inside of L, then we should have no dupe X colon L. And for this one, there's also a no dupe A version of this. So split. We're going to do the intros here. Intros H. So the H is going to look like this thing, and we want to do the basically know that B is not in L and that L is also not ordered. And the way that no dupe is constructed, because it's an inductive data type, we can do the inversion of this assumption to get the two components out. So inversion H, it gets us this gigantic thing. By inverting H, we know that if we think of X and lowercase l as B and L, then we know that the B is not in L and no dupe of L. I don't know why I defined this X and L. We can just get rid of those by doing subst. And so here we have the simplified version. We took this H and we are able to acquire these two components of it, because to be able to build this H, we needed to have proved these two components. And then we want to prove no dupe. So we know that we want to apply no dupe cons, but we're trying to prove both lemmas at the same time, so we can't necessarily apply no dupe cons. We want to apply no dupe cons on this top one, and the no dupe A on the bottom one. I think there's a way to do this. There's a way to do a different tactic on both sides, I'm pretty sure. Like do tactic 1 on the first goal and tactic 2 on the second goal. But if we try apply dupe cons, then it'll be successful for this top one, but unsuccessful for this bottom one. It was successful for the top one, it split it up into this one, and it was unsuccessful for the bottom one, so it left it alone. So we can just do try, and we're just applying the same thing on both sides. I apply no dupe A cons. That simplifies the bottom one as well. And now everything is just something that we have in our context. Or rather, we need to convert from the in A to the not in A. So for the no dupes, we can convert it via the induction hypothesis. So we can just do for these no dupe goals, we could do a try apply IH, and that converted the no dupe goals into the opposing thing, which we should be able to be resolved by auto. So that solved those goals. And now we want to prove that this in A corresponds to the in B. So we do have this in A already defined over here, so we can just do a rewrite with that. Rewrite in A in. That didn't work because we wrote in one way, but we want to rewrite it in the other way. So we could do a try in here. But if we do a intro H4 instead, oh, actually, I was only applying it to the one side, so I was doing the rewrite in the wrong direction anyway. But if we do an intro H4 on both sides, then we have these things. Then we want to apply H2 on both sides. So now we have the flip version. We want to prove in to in A. Now instead of rewrite, we can do an apply. Which gives us exactly what we want to prove from the H4. So auto should be able to finish off both proofs at once. So here we have this gigantic chain combo. We're like essentially 4 different proofs at the same time with just one tactic. And we chained them all together and completed the goal automatically. That's pretty darn cool. This is definitely not the best method to go about this, but it is pretty fun. The fact that you can do these kinds of proofs like this is very fun. And once you have the proof, it doesn't matter how you constructed a proof. I guess some proofs are better to maintain than others. Like if something goes wrong, if one thing breaks in here, then it might be harder to fix this kind of proof because you'll have to do more stuff all over again. So I definitely don't suggest this kind of thing. But it works. And if it works, it works. So we're done with this proof. And just to make sure, we have this one is done, this one is done, and this last one is also done. And from those helper lemmas, we are able to prove that the helper lemma, that the strict subset implies that the cardinality is less than. And from this helper lemma, we were able to prove our method for inducting over graphs. And that concludes what I wanted to cover in today's video. It worked out pretty nicely where we were able to define the ordering of nodes to be able to create a set of nodes and use that to define our graphs. So now that graphs are equal as long as they have the same set of nodes. Even if the nodes are in a different order, it will still say that they are equal. The rest of the stuff, like the edges, doesn't have an ordering. It's just a function from edge to bool, so there's no list of edges. So that is fine. So yeah, the graphs are going to be equivalent whenever they have the same nodes and edges, and there's no modulo in equivalence of the nodes. Then we define strict subset as it's a subset in one direction but not the other direction. And from that strict subset, we define a whole bunch of helper lemmas to convert into the list representation. And we proved our final thing, that the strict subset implies that the cardinality is less than. So even if we changed our definition of strict subset later on, if we need to, as long as we prove this lemma for our new definition of strict subset, we should still have the same graph induction. So as long as we have strict subset, P of G, basically our induction hypothesis is operating over all strict subsets of the graph, and we're able to construct a proof of the thing greater than that. And then we have a way of doing induction. We have a way of proving P of G for any G. And we're done. Thank you for watching this video. I guess I should explain. Next time we're going to try to prove, I think we're going directly into trying to prove this thing down here, that either a path exists or a path doesn't exist. And we're going to be doing this by induction over G for all A and B. So if you think about it, to prove that there is a path from A to B, we want to show that we can build a subgraph by traveling down one of the neighbors and removing the. Let me try to explain this again. So we want to prove that there's a path from A to B in the graph G. So we construct a graph that does not contain node A, and that is going to be a subset, so we know that the paths are decidable within that graph. Then we use that to be able to query, is there a path from one of the neighbors of A to B within this subgraph? And if we know if any of those are true, and we can reconstruct a path within the larger graph G. So next time we're going to be, I guess we aren't really there yet to be able to prove this entire lemma, but we're going to construct a subgraph by removing all of the one particular node and removing all edges associated with that node from the graph, and prove that this is a subset of the other graph, and that any paths from the smaller version can be converted into paths of the larger version. And that should be getting us really close to this path beside thing that we want to prove. So thanks again for watching, and I'll see you guys next week.